Good day to all of you. Myself, Dr. Arvind Sharma, Associate Professor in Physics, Government Dover College, BIKANER. Today, we are going to learn about the topic, the rigid rotator with free axis. This topic is not in your syllabus, but the solutions of this problem is exactly the same as hydrogen atom. So this topic is important for you, important for your NET classes, NET exam. Okay, so just a few things, if you learn, you understand this topic. And also in hydrogen atom problem, the solutions of rigid rotator type are also used. So both questions are, you can easily understand, and this is helpful for your NET exam. The rigid rotator with free axis. The system consisting of two spherical particles attached together, separated by finite distance and capable of rotating about an axis, passing through the center of mass and normal to the plane containing the two particles, constitutes a rigid rotator. See this figure, particle M1, particle M2. This is center of mass axis. Okay, so these are two spherical particles at a finite distance, and these particles are capable of rotating about the axis, which is through the center of mass and normal to the plane. So such kind of geometry is known as rigid rotator. If these two particles are constrained to remain in one plane, then the direction of the axis of rotation is fixed, and the system is called the rigid rotator with fixed axis. Why this is known as rigid rotator with fixed axis? Because particles are constrained to remain in one plane, then the direction of the axis of rotation is fixed. Okay, if the plane of these two particles can move, then the axis of rotation is free to take any position in space. So the system is called rigid rotator with free axis. In a diatomic molecule, the atoms vibrate with respect to each other, and so the distance between atoms will not be always constant, while the distance apart of the equilibrium position is constant. Thus, the system of diatomic molecules is not really rigid. The system of diatomic molecule is not really rigid. However, it may be treated at least as a first approximation as a rigid rotator with free axis. In approximation, we can take it as a rigid rotator with free axis diatomic molecule. Energy of the rotator. The kinetic energy of a particle of mass m can be expressed as T equal to half m x dot square, y dot square, z dot square. X dot, y dot, z dot are components of the velocity of a particle along x, y and z axis, half mv square, and these are components. Okay, the transformation between Cartesian coordinates and spherical coordinates are given by, we know, x equal to r sin theta cos phi, y equal to r sin theta sin phi, z equal to r cos theta. Okay, now using spherical polar coordinates, kinetic energy converted into the T equal to half m r dot square plus r square theta dot square plus r square sin square theta phi dot square. If the distance r of the particle from the origin is fixed, if r is fixed, then its derivative r dot equal to 0. Then the equation converted into T equal to half m r square theta dot square plus sin square theta phi dot square. taking the center of mass of the rotator as origin, the kinetic energy of the particle of mass m1 is given by T1 equal to 1 upon 2 m1 r1 square theta dot square plus sin square theta phi dot square. Similarly, kinetic energy of mass m2 is T2 equal to 1 upon 2 m2 r2 square theta dot square plus sin square theta phi dot square. Total kinetic energy of the rotator will be summation of T1 and T2. T equal to T1 plus T2. It becomes half m1 r1 square plus half m2 r2 square theta dot square sin square theta phi dot square. As there is no potential energy of the rotator, hence the total energy is just kinetic energy of the rotator. Okay, so your equation of total energy for rotator becomes E equal to half m1 r1 square plus half m2 r2 square theta dot square sin square theta phi dot square. Here m1 r1 square plus m2 r2 square equal to moment of inertia I of the system about the axis passing through the center of mass and perpendicular to the line joining the two masses. Now the equation becomes E equal to T equal to 1 upon 2 I theta dot square plus sin square theta phi dot. The moment of inertia of the rotator may be expressed in a more convenient form. We know that center of mass is given by RCM m1 r1 plus m2 r2 upon m1 plus m2. Now if RCM equal to 0, then this is 0 equal to this, and the condition becomes r0 equal to r1 plus r2, so r2 equal to r0 minus r1, and substituting this in equation 8 we can easily obtain the solution relation for r1 and r2 in terms of r0 and r0. r1 and r2 in terms of r0 and m1 m2. r1 equal to m2 upon m1 plus m2 r0, r2 equal to m1 upon m1 plus m2 r0, r0. So moment of inertia m1 r1 square plus m2 r2 square. Moment of inertia of the rotator I equal to m1 m2 upon m1 plus m2 r0 whole square plus m2 m1 upon m1 plus m2 r0 whole square equal to m1 m2 upon m1 plus m2 r0 square. So I equal to mu r0 square, where mu equal to m1 m2 upon m1 plus m2 is known as reduced mass of the system. Mu is reduced mass of the system. From equation 4 and 7, it is evident that rigid rotator behave like a single particle of mass mu. A two-particle system, rigid rotator behaves like a single particle of mass mu, placed at a fixed distance equal to unity r equal to 1 from the origin, which in this case is the center of mass of the system. Wave equation for the rotator. The Schrodinger wave equation is three dimensions in spherical coordinates. This is the equation which we written in last video for spherically symmetric potential. Okay, this is same del square in terms of r theta phi, and this is the second term. For a rigid rotator, we have seen that potential energy is 0, r equal to 1, and the mass m may be replaced by the moment of inertia I. Therefore, the Schrodinger wave equation for a rigid rotator becomes mass replaced by moment of inertia, and r equal to 1, so there is no term for r. Okay, only terms for theta and phi. 1 upon sin theta, del upon del theta, sin theta, del psi upon del theta, plus 1 upon sin theta, del to psi upon del phi square, plus 2i upon h bar square is equal to 0. Okay, this equation consists only theta and phi. Solution of wave equation. Eigenfunction for the rotator. Psi theta phi equal to theta, capital theta and capital phi. Okay, so equation becomes the technique of separation of variable. This technique is known as separation of variable, and this equation becomes like that. This is theta term and second part is phi term. Okay, so you can take the phi term on right hand side and left hand side is theta term, and same argument, left hand side is function of theta, right hand side is function of phi, but both are equal only the case when the result equal to some constant, and here we are taking the constant as m square. Now equation becomes for theta and phi. Phi is a simple equation, del 2 capital phi upon del phi square plus m square capital phi equal to 0. So capital phi equal to a e raised to iota m phi. Capital phi equal to a e raised to iota m phi. M is 0 plus minus 1 plus minus 2 etc. We can easily calculate the normalization constant by using the normalization condition, integration 0 to pi phi square d phi equal to 1, and the value of a equal to 1 upon under root 2 pi. So the normalized wave function phi m, capital phi m 1 upon under root 2 pi e raised to iota m phi. Multiplying equation of theta term. This is the equation of theta, and we just rearrange it by multiplying capital theta upon sine square theta, and this equation becomes 1 upon sine theta delta capital theta upon delta theta plus 2i e upon h bar square minus m square upon sine square theta capital theta equal to 0. Let us now define a new variable x such that x equal to cos theta, sin theta equal to under root 1 minus x square. Okay, so capital delta theta upon delta theta becomes this. So you can easily convert this equation into x. Okay, del upon del x 1 minus x square delta capital theta upon delta x plus beta minus m square upon 1 minus x square capital delta theta barabar 0, where beta equal to twice I e upon h bar square. Equation 28 is known as Legendre's equation, and it has physical significance only for values of x between minus 1 and plus 1, because what is x? Cos theta, and cos theta values are minus 1 to plus 1. For convenience, its solution theta capital theta equal to 1 minus x square raised to m by 2 x like as a Legendre equation solution. Okay, if we use this equation in this equation, so it becomes, we are calculating that this is only maths, you can easily do, and using these equations and dividing this and simplifying this using alpha and lambda. Alpha equal to m plus 1, lambda equal to beta minus mm plus 1. This is the equation, simplified equation. 1 minus x square capital X double dash minus twice alpha small x dash plus lambda x. Now let us assume that xx may be expressed as a power series. X equal to a0 a1 plus a1x a2x square plus a3x square. Similarly x dash or x double dash. First derivative, second derivative, and by replacing this equation here in order that the series may be 0 for all possible values of x. The coefficients of individual powers of x must vanish separately. That is, in general, this equation becomes like that, and an plus 2 equal to twice n alpha plus nn minus 1 minus lambda upon n plus 1 n plus 2 an. So recursion relation an plus 2 upon an equal to n plus m plus 1 minus beta upon n plus 1 n plus 2. This is called recursion formula for the coefficients in power series of x. This is called recursion formula for the coefficient in power series of x. In order to obtain a satisfactory wave psi, it is necessary that xx should be a polynomial breaking off after a finite number of terms. As in the case of harmonic oscillator, the series will break after nth term if the nominator of equation is 0. Its nominator is 0, then the term will break after the nth term, and by using this, your value of beta n plus m plus 1, and n plus m is L, and beta equal to LL plus 1. So using the value of beta LL plus 1, that means the whole mathematics done due to this beta, and we got the small result beta equal to LL plus 1. Del upon del x 1 minus x square del capital theta upon del x plus LL plus 1 minus m square upon 1 minus x square theta equal to 0. The solution of this equation contains the factor associated legendary function. Associated legendary function PLMX, and PLMX is defined as 1 minus x square raised to m by 2 dm PLX upon dx raised to m. So the solution of this equation, capital theta equal to B PLMX, B PLM cos theta. According to orthonormal properties of Legendre's polynomials, integration equal to 0 for k equal to not equal to L and equal to this value for k equal to L. According to normalization condition, integration theta ml square d theta equal to 1. Okay, so B becomes B equal to under root 2L plus 1 upon 2 factorial L minus 1 m upon L plus m. Using this, capital theta equal to under root 2L plus 1 upon 2 factorial L minus m upon factorial L plus m PLM cos theta. So your function becomes psi equal to theta phi, and this is the product, that is your rigid rotator wave function psi ml 1 upon root 2 pi under root this term PLM cos theta e raised to iota. Eigenvalues or energy levels of rigid rotator. From this we have 2IE upon h bar square equal to LL plus 1. So your energy eigenvalue becomes E equal to EL equal to LL plus 1 h bar square upon 2I, where L equal to 0, 1, 2, 3. This equation gives allowed values for the energy eigenvalues of a rigid rotator with a free axis. Okay. So next topic is rigid rotator in a fixed plane. If we consider the rotator to be only in xy plane, then theta equal to 90, and your equation becomes very easy. Del 2 psi upon del phi 2 plus 2I E upon h bar square psi equal to 0, and solution psi equal to phi m, and this is very simple solution of phi which we already derived, and your energy eigenvalues are given by E equal to em m square h bar square upon 2I. So these are the results for rigid rotator. In next lecture we try to understand the problem of hydrogen atom. Okay, thanks to all of you.